this is the last slide. I haven't presented with this these before. Okay, that's better. Great, apparently you can ask questions. I have no idea. Alright, so yeah, I came here to talk about the new typing support that's coming to Python. So how many of you have looked at that, or have any familiarity with that, or interest, or anything? How many of you have used a typed language like, well, Java, or Haskell, or Camel, or anything like that? Okay, so that's good spread. So some of you, hopefully, most of you will be at least somewhat familiar with what a typed language can do. And yeah, so the big news is that like Python historically has already been a dynamic language, and it has, it's prided itself on that, like duck typing, flexibility, metaprogramming, all that. So static typing is kind of like foreign to it, and okay, now the slide is one of yeah, so most of you will probably be familiar with the motivation for static types then. It gives you all these, well, it results in safer code, which is, most of you will be familiar with that. That's the usual advantage which languages like Java are going to give you. But as you might be familiar, in a language like Java or those verbose languages, typing can be pretty inconvenient. It can slow you down, it can be a lot of extra work, it can be, it can be pretty painful. And if you have a good typing system, which is like a gradual typing system that Python has, it can be quite a different experience. It can be a very interactive experience. It can make your work faster. It can make your work easier. It can make activities like refactoring very faster, or much better and more convenient. And yeah, so if you're familiar with most good code, you probably know that it's considered good style to document the types of the inputs to function results and everything like that. So that's the other aspect of it. If you're already like documenting your functions with the types and annotating them, why not actually check that? And that is the other aspect of typing. You can consider it as machine verified documentation. And documentation that doesn't just become verified, but becomes a tool to check the correctness of all the code that uses it. So it's actionable documentation. So the first thing, I'm going to start with some theory and then get into the more practical fun bits. This is just to set the context. People talk about type systems very loosely sometimes, because most statically typed languages, they begin with a type system defined right at the start. So you have something like Java. People don't talk about the Java model or the type model. They just talk about, okay, it's Java, it's typed. But if you look at types in general, what's actually happening is it's a kind of model verification. So anytime you have a type system, you have these three things. You have a semantic model, and the semantic model is it's a simplified model which you can consider and construct at compile time of how a program might behave, the same way that you might have a model of a physical system. And the model can be very simple, or it can be extremely complex and powerful. And to give you an idea what's meant by a model, it's checking constraints such as what the possible values is that a variable can have, what the possible inputs and outputs are of a function, and then, for example, checking that, okay, if you call a function at one point and call it at another point, that the inputs and outputs actually match up. So these are properties that the model can statically verify or reject given an input program and some types. So every type system, whether it's explicit or not, has a certain model. So it's worth actually asking and defining what the model is. And the reason this is important is in Python is because Python didn't come with a semantic model. So up until this point, there were like several competing semantic models with different trade-offs and different strengths and weaknesses and what they check. And the one adopted by MyPy, which I'll get to later, that's the one that kind of has been now adopted as the official semantic model that will be used for Python typing going forward, or at least the the built-in static typing. So then the second part of any system is you need to be able to actually decorate and annotate your code with the intended types. Because you need to have the types are what the model checks and verifies against. So you have some languages where you can actually end up putting no explicit type declarations into the program because the type system is smart enough to infer it. So if any of you have worked with Haskell, that's an example of a language where you can actually never mention a type anywhere, but your program is still completely statically typed. So you have explicit declarations and annotations with a type system usually, and then optionally, depending on the language and the system, some degree of inference. And then lastly, all of this doesn't mean anything unless you have the tooling and systems to actually do the checking against the model. So yeah, report errors obviously. So in Python, the semantic model is defined in PEP 483. So there's actually two PEPs to this. People talk about PEP 484 as the typing PEP, but PEP 483 is actually the foundation that defines the semantic model that Python uses. So that goes into like a formal definition of like, well, it's like a mathematical definition of what the types are, how they relate, what the declarations mean, how that relates to runtime behavior and back, and everything else like that. And then PEP 484 actually defines the syntax, which the model is then checked against. And then lastly, the tool to actually do this is not something that's distributed with Python at the moment. So your Python interpreter is not going to use or do anything with these type annotations yet. But MyPy, which used to be a third-party tool, is now the blessed and official type checking tool for Python. So before I dive into the depth of it, I want to give you just an idea of what this looks like in Python. Firstly, to use it, if you want to play around with it, it's actually pretty easy and simple to get started. You can start your virtual env and you just install that package, mypy-lang. And I just want to mention this as a kind of like a gotcha beforehand because there is a separate MyPy package, but that has nothing to do with the type checker. That's actually some WSGI thing. So your first step, if you were to install MyPy, is you're just going to be confused. So just be aware of that. Install mypy-lang. That's the one you're looking for. And once you have that, you can just invoke this on any source code. So just like that, MyPy source code, it checks the types and it can generate reports, you can do all kinds of things, you can tweak the things, you can point it at stub files. It's pretty powerful, but you don't have to do any of those things to get started. You can literally just point this at any existing program and it will actually be able to check a whole bunch of that program already. So you can start getting benefits from type checking in Python today without adding any like annotations or types to your code. It can already check quite a large degree of code. Okay, so that's an important point that I mentioned earlier is that the types, the model that Python has is gradual typing. So if you've ever used a system like this, you know some languages are completely typed, like Haskell, where everything is typed, and most other languages. And then some dynamic languages have been defining these gradual typing systems where you have an idea of partial type information, where some parts of your program is typed, some parts are untyped, and MyPy works like that. So if you use the standard library, for example, those calls will be checked and typed, but your own code might not be typed until you add some annotations. Then you get increasing benefit from it as you add annotations. It's a bit like adding test coverage. I'll talk more later about the relation between types and tests.
Sorry, from which version of Python onwards does this work?
MyPy actually checks both Python 2 and Python 3 code. So the annotation syntax defined in PEP 484, that is, it uses the function annotation syntax, which is Python 3.3, yeah. But that's not required. You can actually use type comments to replace that and write type comments in a way that's actually still Python 2 compatible. So you have like specially formatted comments, which you'll see later, which contain the same information. It's kind of like a bridging system for older code.
Okay.
So when you run Python, there's actually a command line flag which tells it to kind of like look at the code in Python 2 or Python 3 mode. So yeah, you can even use this with Python 2. You just want to get quite the kind of like same depth of checking.
I'll just try. You can't install it with Python 2 yet. refuses to install.
You have to run it on
you have to
Python.
run it on Python 3, but you can't point it at Python 2 code.
Oh, okay.
Cool. So here's your basic Hello World program with types, and the type annotations are the bits in the blue. You've seen, like previously, those they weren't defined to actually mean typing. They were intentionally left undefined. So when they were introduced in Python 3.3, the idea is, okay, here's this feature. It's neutral. It's probably going to be used for typing, but it can be used for anything else the community comes up with. And now the idea is that they're proposing, okay, let's just use this for typing and standardize on that. So unless another compelling reason comes up to keep supporting other uses of annotations, this might probably become the de facto standard usage of annotations, and the other usages might fall away and get deprecated. So yeah, what this does is, just in case it's unclear, is you have your function argument there, the name, which has been declared with that postfix colon as being a string, and then at the end there, the result of the function is also being declared as a string, and then the code around is checked. So if you have code like this, then you can have a program like greeting will, that will run okay, it will pass the type checker because you're passing a string, but the second program will actually give you that type error over there, where MyPy will tell you that the first argument is an int, not a string. You can't add an int in a string. And it does this without actually running the code, without needing unit tests, without anything else, just pure static analysis. So that's a powerful thing. It will also check, obviously, the return result. If you try and use the return result the way that isn't type compatible, it will blow up about that. And one thing I should mention is that you can actually leave out those the type annotations I just gave. You can actually leave them out. I made them explicit here, but because you have a string that you're adding to another string, MyPy knows that the name has to be a string as well, and because you're returning the result of that, it knows the result of the string as well. So you can actually leave out those type annotations, and it will still infer that those are string and string. So it's an example of how the gradual typing and type inference of MyPy is actually quite sophisticated. It's, for example, more sophisticated than the limited type inference you'll see in some other languages, which have like the var bindings, but it just does local inference. Like Go does some basic inferences, C# and so on. But MyPy will actually do kind of like inference across all boundaries and stuff like that, which is pretty powerful. So it's somewhere in between Haskell and Java if you've worked with both. It's like you get more inference and more power, but not quite as much as a language like Haskell, but not as little as a language like Java or C#. So, and this is just, I don't know if you can read that, it's a little bit small, hard to fit in, but this is a more complex example to show you just how powerful the inference can actually get. So here I made a little, have any of you used Twisted or asynchronous frameworks in general? Token 2 or 3 Twisted users. Okay, have any of you used promises or futures or stuff like that in JavaScript, or read about them at least? You add callbacks and stuff. Okay, so up there I have a deferred type which represents a future value that you can add callbacks to. And this is, that's like a toy implementation of one, which is not on the slide, but it's parameterized with 2 types, the input and the output type. So this is a deferred taking an int, returning an int. And what I'm doing then is I'm adding a whole bunch of callbacks to that. And without actually having to specify any types on those callbacks, MyPy can actually infer that the first argument is keeping the type from int to int. The second argument is trying to call string. Actually, I modified that. That's supposed to be minus. Yeah, but like if the second argument tries to actually subtract a string from an int, for example, you'll get that type error. Incompatible types for string and int. Oh, sorry. Yeah, this error is supposed to line up with this line. Sorry for the confusion. Yeah, so what's happening there is you first multiplying the number by 2, then you convert it into string, then you're trying to subtract 5 from that number. And that gives you a type error because you can't do that, but you didn't actually specify any of that information. MyPy is inferring that flow of types as it goes through the string of callbacks. If you remove that string conversion, the code will type check again. And then here again you'll see there's more stuff that happens. All that code, even across the length call and the +1 call, the type information gets preserved. There at the end, print gets done, that works. And at the end, you'll see there's another erroneous callback where you're trying to double result of nothing, because print returns nothing. And MyPy is smart enough to infer that it tells you that you're trying to use the result of a function that doesn't return a value. Yeah, and then finally, if you actually try and use the callback, you can call it back with an int, which is the expected input type. It works fine. If you try and call it with a value that isn't an int, it gives you a type error. Cool, so that gives you an idea of the kind of more complicated types and inference that MyPy is actually capable of doing. So you can get very far with very few type annotations and spot quite a large degree of semantic and logical errors in your code. Cool, so now I'm actually going to get into the depth of how PEP484 works and how you actually use it in your code to define things like what I just showed. So the basic syntax is function annotations. That's defined in PEP 3107 if you want to read more about it. That's what was introduced in Python 3.3. And these are some types for some of the built-ins in Python that you're already familiar with. So you'll see like len, for example, takes any sized value, which means that's an existing generic type, by the way, which means anything which has a len method, effectively. And it returns an int, which is the length. Repr obviously takes any object to a string. Hasatter takes any object, name has to be a string, and it returns a bool. And then print is an example of quite a complicated function with a bunch of different things. And you'll see that's how you combine arguments which have types and default values. You actually have the name, the type, and then equals and the value. So if you had a complex call interface like print does, that's how you would define it. And you'll see that even if your function doesn't return anything, you still are explicit about it, annotating that it returns a none, like that.
So what's the difference between any and object?
I'll get to that right now.
Okay.
Cool. So yeah, the next thing is those annotations work for function arguments and results, obviously, but you want to be able to annotate the types of variables as well. So currently Python has no syntax for that, so here you have to use type comments. And this is how you do them. They have a special format. On the same line as the definition, you have a comment, type, colon, and then the actual type. And even though this is in the comment, MyPy and other tools will actually go find it and treat it as a type annotation. So you can have a basic type like a string, you can have a parameterized type, list of int. This is an example of where a type is actually necessary and can't just be inferred. If you have a literal list with some integers in it, then MyPy will actually be smart enough to infer that that value is a list of ints. But if you have an empty list, it doesn't know what the element type is. In the case of an empty list, that's an example of a case where you will actually usually define the type, even though you are giving a literal value, and you won't just rely on the type inference. Yeah, and then finally, these are not just limited to built-in types; it could be any arbitrary type. So if your code has some query type which has a parameter for the type of value being returned, it might be like a query for a user. You might have something like that.
So why would you need that first line? Since x equals span, surely that type is already string.
Yeah. So in the first example, that's an example of a type which is actually optional. You don't have to specify that MyPy will infer it because you have a literal which already has a type. So that's a good principle to explain how the inference actually works. Is that you start with the values of known types, which are generally literals, or any other code which has existing annotations, and the type information basically flows through those. It flows as far as it can until it hits a dynamic boundary, which the type system can't see across without actually executing the code. But it can get pretty fast. So things like literal assignments like that, you usually don't have to give out any annotations. Only in cases like, for example, with an empty list, where the type of that will actually only get realized once the first element gets appended. So statically, you have to just give it that extra little hint to tell it what you intend the future element type to be.
Right. With the arrays, it's the whole array will then begin to a string, like Java, for example.
Yeah.
So you can't combine into strings.
Yeah, that's correct. So you can have an untyped list. So you can get there. You could have just said type list, and then it would be a list of any. In fact, it would just be expanded to list any, the same any you saw previously, which means any type. But if you provide the type parameter, then it gets the type of the element gets constrained, and all the methods of that list will actually return and expect values of that element type. If you try and pass an inappropriate or incompatible type, it will give you an error. So if you're familiar with generics in Java, or parametric polymorphism in a language like Java, like Haskell, sorry, it's the same kind of idea. And later we'll get into how you actually define those. So one thing that's coming in the next version of Python precisely to fix this current problem is variable attribute annotations, which that's defined in PEP 5.2.6. It's coming in the next version of Python, and they look like this. So it's pretty much the same as the the function argument annotations. You have a variable colon type equals a value. You can also have a type declaration like that without any initializer. So you can statically declare, okay, X will be a string, but then only assign to it later. So these become like type declarations that you can just use anywhere. And in the PEP, I'm not going to cover it here, but in the PEP they also cover a few other example, more advanced cases. Like for example, you can actually put these declarations at the class level now, and declare the instance variables that class will have, and the class methods and variables that the class will have, without just kind of like not just having it in your init.py. So if you've ever used the library attr or stuff like that, where you declare stuff, instance variables at the class level, this is now becoming a little bit more blessed, where Python actually gains the ability to statically declare class members and types and stuff like that. So there's quite a bit in 5.2.7 beyond this, but this is the main important thing that it gives, or that it enables. So you don't, once this hits, you won't have to rely on the type comments to type your variable to find this. Cool, so cool, so the types that are actually supported by the type system is everything listed here. So obviously classes are supported as types. They're the main existing type. So that means any built-in classes, any user-defined classes, you can use them as is in any type expression, and it'll pretty much do the right thing. You can also use abstract base classes. If you've looked at the ABC module, how many of you are familiar with Python's abstract base classes and the whole interface support that allows everything? Okay, so those work as well, and they get treated a little bit different from concrete classes, but all the same kind of like instance check and membership checks that abstract base classes provide you. They actually work as is in the time system. If you're not familiar with them and you're familiar with interfaces in a language like Java, it's basically the same idea, more or less. That's the intuition of it. Then the new typing module, which is introduced in PEP 4.8.4, that introduces a number of new special types, like any, and a couple of others which I'll cover just now. And those you can also use in any typing expression. Then finally you have, ultimately you have generic types. Those are ones like list, that I showed before. Dictionaries, there's a whole bunch of types that actually take type parameters which get used for elements or parts of it, or inputs or outputs. And you can define your own ones. So you can define your own tree type with an element type that is generic and characterizable. And those you can use as types, even though they're not actually concrete classes. And then finally, the type system supports a couple of nifty features, like type aliases, variables, new types, which allow you to actually express type information beyond what can usually just be inferred. So you can actually build extra type information into your system, which doesn't exist at runtime, but that gets very fun at compile time. You can increase the safety of your code. Cool. So to go through the special types that the typing module in PEP 4.8.4 provides, the first one, the most fundamental one, is this any type. So any literally just means anything. It's the most generic type possible. If you've looked at any type system literature, you might have heard about like type lattices, the top type, the bottom type. Any for Python is the top type in the semantic model of the type system. So every other type is a subtype of any, and it's compatible with every other type. So it's the least amount of information you can have about a type. If you just have a Python, or if you just have a program with no annotations, then everything is just of type any. And so it's the most general possible type that tells you the least about your program. So what you do when you add gradual type information is you take this any type and you narrow it down in various places. And by narrowing it down, you reduce the scope and complexity of your program at that point. Cool. So, there's a couple of basic types that get provided by the module as well. Ones which you don't usually specify explicitly. So tuples have a syntax like this, where they use a special tuple constructor, and that actually takes an arbitrary list of types as the parameters. Unlike, you'll see that a list only takes a single element type, because a list is a collection of homogeneous values. Tuples, on the other hand, they're like an anonymous structure of differently typed values. So if you have a tuple like that, with a 1 and a 2 and a 3, that gets inferred to that type over there. It's a tuple of an int, a float, and a string. And in this case, it will actually be inferred, but if you wanted to write it using the new annotation syntax, you could actually write something like that. Then you have callable, which if you've used many other languages, it looks quite a bit unwieldy. It's a bit verbose. It's not the nicest thing, but it's there, so we have to deal with it. And that looks kind of like that. You have a list of input arguments for the function, and then a final value, which is the result type. So as an example, the length function, its signature would look like that. It's callable of any sized value to an int. So once you have it annotated, if you want to have another function which accepts a function of that signature, that's how you would specify it. Cool, and then there's a whole bunch more, which you can go look in the typing module for.
Sure. Question about the tuple. That's in the definition you had, like the int, float, and string. Now, would you be able to add more elements to that, or how would you? Does that dynamically add it, or is it?
No, they're static.
Is it next static?
Yeah. So in Python, the tuples are actually immutable. So you can't actually modify or append or do anything else like that. The only thing you can do is construct a new tuple from the old tuple.
Okay, so you can't even replace the elements inside it?
Yeah, no, you can't.
Okay.
There is, however, things like name tuple, and you could create your own kind of like a mutable tuple class, which is just a structure with a couple of swaps each of the time. And then you could do the same thing. You could have like one for 1 element, 2 elements, 3 elements, 4 elements, just define however many you want to. And then you can actually use it just like this, but also modify it, mutate the values, but not mutate the types. So you could have something with a certain signature, like this one, int float string, and you'd be able to modify the float value, but you wouldn't be able to assign an int or a string or anything else in there.
In the base tuple now?
No, if you had your own your custom user defined ones. Yeah. So most of the you'll know that Python already has the types module, which has a whole bunch of type representations for Python's built-in types, like dictionary, list, set, all of those things. However, they don't, the base ones you can actually use directly as types in MyPy, but they're not parameterized or generic. So the typing module provides parameterized versions or generic versions of all these buildings as well. So that's, for example, list with the element type, IEEE with the element type, dictionary with the key and the value type, which may differ, and set with the element type. And there's a couple of more, like there's typed versions of name tuple, if you're familiar with that, and so on and so forth. But they all kind of follow the same pattern, so I'm not going to look at them individually. So then the next special type, the next special primitive type that PEP4 supports is this union type. So if you're familiar with Haskell or languages like that, the ML family, you have this idea of some types A union in Python is a sum type like that. And if you're familiar with different kinds of sum types, it's specifically an anonymous one. So you can declare a variable to be a union of a set of types, which means that it can have any one of those values. So you're not limited to declaring that a value is only a string or an int, like you are in a language like Java, say, you know. You can actually say, okay, this variable can contain an int or a string or a list or a UUID key from the database or whatever else, and you can actually keep track of all that information. And this is not something I have a code sample for, but to give you an idea, you can have a function which takes a value which can be any one of 5 different types, and then in your function, as you do type checks, the control flow actually gets refined. So you can take this value of a union type and say int string float, and if you have if x is instance of string, and you enter the if block, inside that if block, the value now is a string. Because you've done the type check, and MyPy actually carries that type information forward. And then inside there, you don't have to cast it or do jump through hoops to convince the type system that things are okay. You can just use it as a string. And in the else block, it will actually not be a string anymore. So the union type in the else block will actually be refined to not just int string and whatever else. The int option or the string option will be eliminated, and you have a union type with the remaining values. And then as you go through refining your checks, every branch and leaf and logic of your program actually gets verified, and the union type gets narrowed and widened as things go through control flow. So this is actually a very sophisticated feature. An example of this is the optional type, which is just a simple alias for a union of a type and none. None represents its own type, by the way. So this means if you have any value which can either be none or a string or something like that, you can just say optional string instead of writing out the full union. And then, that type information will be carried forward. So your code can be very safe. You can, for example, if your constructor to some function takes either a string or a none, and you need to check that default before you use it, then the type system will verify that for you, because if you try and take that, the optional string, if you try and add that to another string, it'll give you an error and say that, string is not compatible with optional string because it may still be a none. But if you insert a bit of code which says if string equals none, then string equals the default value, then after that point, it's no longer a union of tier none, it's just a string. So, the type system can actually make sure that you have the appropriate dynamic checks to not run into a situation where a value which may still be none is treated as if it's not none. And if you've ever had code blowing up because a none got into a place where it shouldn't be, or a none wasn't checked, this is exactly for that.
Like the Haskell maybe, or is it different?
It is exactly the same idea. The only difference though is that union is not a reified type. So in Haskell, you have an explicit maybe because Haskell has distinguished sum types. It doesn't have anonymous sum types. In Python, because Python is a dynamic language, anything at runtime can be any type. So you don't have a separate first-class value like a first-class data constructor to distinguish nothing and just. You just have at the type level a union of none and the value.
Okay.
And the type system will carry that through, and when you do the appropriate checks, it narrows it down, and then the type is no longer union. So it's kind of like a compile time only maybe compared to Haskell. But it's the same idea otherwise. Cool, so the next feature that the system supports is type aliases. And if you're familiar with type aliases in Haskell, exactly the same idea. What a type alias is just another name for an existing type. And that can be very convenient once your types start getting very long. And as you'll see, that the definition of them are very natural. Like, you can get a type alias for an existing value like string and call it URL, and it's still that URL type is now a first-class type which you can mention any way you can mention the type, and it will act as if string is there. So it works exactly like a string. It's interchangeable with string. It's purely a human documentation tool which you can now put in your types and in your signatures so that it becomes easier for humans to understand. So if you have a function which takes a, instead of having a function from, like, let's say you have something to obfuscate a URL or to decode it, instead of having it be URL or string to string, you can make it URL to hash or something like that. So your types can become more descriptive, more human friendly, without changing anything about the semantics or costs of the underlying type system. So that's the one case where aliases are useful. And then the other case is just where you have longer and complicated types that you just want to give a more convenient and easy to use and easy to reference name for. So instead of saying list int all the time, you can say int list. Or you could call that numbers or something. You can give it a domain specific name that just makes the rest of your program read easier. Once you start getting bigger types like point, you can have, let's say, tuple float float. So tuple of two floats, you can consider a point, and if you write some geometric code or stuff like that, instead of writing tuple float float all the time, which will get noisy extremely quickly, you just reference it with a shorthand point. And then the advantage is if you decide to change it from a tuple of a float to float to, let's say, a tuple of a ratio to a ratio, or an int to an int, if you switch to an integral grid system perhaps, you only change the definition of the type alias, and all the uses of it automatically just carry that forward. So you don't have to rename it in potentially 1,000 places, you just rename the type alias, you change the definition of the type alias in one place, and it takes place everywhere that alias actually gets used. And then finally, with things like callable, which they just get long, you can define aliases like that, which just makes things more readable. So if you have a filter function, instead of writing out the entire callable blah 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 blah, you just say predicate, and that's sort of easy to read. Cool, so now the next kind of thing, again, if you're familiar with Haskell, you know that Haskell is both type aliases and new types. And Python with PEP adds the same kind of idea. So like aliases, a new type is a new name for an existing type, but unlike aliases, new types have a distinct identity. They are treated as an entirely separate type by the type system, even though their representation is the same. And but they carry no runtime cost, which is an important thing and a very cool thing. So at runtime, it's exactly the same. This is not going to be a wrapper that exists in runtime, at runtime. Currently in Python, some libraries do that, where, for example, you want a safe string type, you make a subclass of string, and the safe string does some extra stuff to make sure you don't accidentally mix it with unsafe strings. It does automatic escaping, all kinds of stuff like that. Like Django, many web frameworks and templating systems have an idea like this. With new types, you can do the same thing, but with no extra runtime cost or complexity, purely at the type system level. So here's an example where you can use it for units, for example, where you have floats, but instead of having a program with just floats and floats, you can actually constrain those floats to new types which are units, like dimensions, and these can be anything you want to define. In this case, we have kilograms and pounds, and then you have a function to, for example, convert from kilograms to pounds. And what happens when you try and use this is if you try and give it a plain float to this function, it will actually give you an error and say that that float is not compatible with kilogram. But if you just wrap that constructor, the kg constructor, around the float literal, it's like a cost. It explicitly annotates that, okay, this particular literal is in kilograms. So you take the unit information, you make that explicit in the type system. So then you can only actually give things that have been annotated and verified as kilograms as input to this function. And then once you do that, inside the function, sorry, is that a question?
So you can land on Mars. So
exactly, I was going to make that's the other example. Like feet and meters, you don't want to get them messed up. Can be very important. The nice thing about this is you don't have to explicitly unwrap it again, because kilogram is defined as a base type of float. MyPy knows that any value that is a kilogram is also a float, so it acts as a subtype at the same time. And that's a difference to a language like Haskell. Again, if you're familiar with Haskell new types, but so you can see that the kilogram, because it's a more specific version as a float, you can still use it any place which expects a float. You just can't use a float any place a kilogram is expected, because kilogram is more specific. So any float is not necessarily a kilogram, but every 8 kilogram is going to be a float. But once you do this, the type gets narrowed, because you're taking this kilogram, multiplying it, but now you have just a float value, because the most common type of a kilogram in a float is a float. So now you have to explicitly rewrap it in pound, and that decorates the result type as pound, which is now compatible with the output type of this function, and that means you only have to worry about the correctness of this type conversion inside the function which is responsible for that conversion. And everywhere else in your program, you can just annotate, okay, this has to be in kilograms, this has to be in pounds, and anytime you make a conversion error, it'll give you, the type system will give you an error there and says that, okay, kilogram expected, pound given, or vice versa, or whatever your units may be. And then you know, okay, at this point I need to do a unit conversion, and you use a function like this, or you just do whatever is necessary, and you fix the type error instead of having your lander crash into Mars. So, so new types are an incredibly powerful feature, and something that I think once it actually starts being adopted, it's an example of a kind of expressivity and correctness you can get in your program, which you can't actually currently express in Python at all. It's also an example of how the type system it's not just about checking what's already there, it can actually be a tool to enhance the kind of internal consistency that your system has, because you're leveraging the semantic model and extending it to do more increasingly sophisticated checks on your code. And in the limit, if you're familiar with systems like Haskell, you can actually do Turing-complete computation in the type system. Python doesn't quite do that, but as more features get added to the type system in the future, perhaps, it can actually get there. So the next thing is, if you're probably familiar with the problem of forward references in many systems, and that is like for example, Django models. I don't know how many of you work with Django, but you often have to make a reference to a model which isn't defined yet. You have mutual foreign keys between two models, and in that case, you need some way of making a symbolic reference or a lazy reference to another module, or object, or type, or whatever it may be. And that happens with Python types as well. So you would have, let's say, something like draw line, which has the point type, but the point class may not be defined yet. So you're not forced to move all your code below the point class. You can actually keep it above, but if you simply take the type value and wrap it in a string, then MyPy will still treat it as a normal definition. So at any given point, you can kind of make a type reference lazy by just making it a string. And normal Python code will just ignore it because it's always just a string, but the type checker will know what to do with it. And sometimes that's not just a matter of convenience, it's actually a question of correctness, or being able to express it at all. For example, if you have a point method with a method that references point, when these methods are defined, if you know how the dynamic instantiation of Python classes work, the class is not defined yet, and you can't actually reference the class by name until after the class block exits. So this is a case where you have to use the symbolic name of the forward reference like this in order for the class to be able to reference itself directly.
So why does the type system is optional? Why does it need that? I mean,
because remember, up until this point, the annotations were, open-ended. So Python will still go and actually execute all those things. So at the moment, an annotation can be any arbitrary expression, and that actually does get executed in the normal Python interpreter as a normal expression because they're not necessarily types.
Okay.
So normal Python will actually try and resolve that. And with the type information system, it just kind of does nothing. But that could actually be an arbitrary expression that does stuff. This normal Python interpreter doesn't know that. But it's a good thing to raise because one of the points raised in the typing PEP is that once it gets to the point where annotations get standardized on types, they might, in a future version of Python, they might actually change the semantics to make all the reference effectively be lazy. So in that case, you will no longer need the string quoting. It's as if everything works like that. So then you can just have them without strings, and unlike now, they won't get executed at runtime. They'll just be stored separately as annotations. So the need for doing forward references like this might actually go away at some point. Cool. So then finally, any type system has some way of overriding and breaking it. or in some cases just doing something that the type system is not smart enough to see. And in Python, that's the cast operator, which looks like this. It looks like a function. At runtime, it does nothing. At compile time, or at type checking time, I should say rather, it takes a value of some type and just forces it to be another type. So you can use this to make invalid type declarations. Like you can say, for example, t equals cast int, and then give it a string, and then the type system will fully consider that value to be a string or an int now. And sometimes that might actually be the case because you have a variable which might be, dynamically typed, reference multiple types at different times. It can be subject to dynamicity and magic and metaprogramming, which the Python semantic model, the one defined in Delport 3, doesn't actually know about or can't track. So just like you sometimes have to actually give it additional information, a hint, like with an empty list, to just give it that hint of what the empty element type is. In the same case, in some places where the inference currently falls short or where complicated things are happening, you can just give that extra nudge and kind of like manually override the type inference and type compatibility at a certain point to just make it do whatever you want to do. So yeah, that's obviously a feature which you don't want to overuse because you can kind of like just break your program and declare invalid types, and then there's no point in using the type system. But it is sometimes a tool you need. And yeah, the important thing to point out about that is that it doesn't do anything at runtime. It doesn't actually check or convert, cast, or do anything. So you can't use it as a replacement for, like when you call int on a value. That's also in a way a cast. Like you have a string and you call int on it, you get int back out. That's a runtime cast, effectively. It does a runtime conversion. If you do a cast like this, it doesn't do anything at runtime. It doesn't actually go and convert the string to an int for you. It will just take the string and think it's an int and then crash when you try and use it as an int. But you would effectively be turning off the type system, warning about it if you just cast it like that without actually doing something clever or sensible with it. So that's there when you need it. Cool, so here's where it starts getting more interesting. If you're familiar with Haskell, you know that many languages support this idea of parametric polymorphism. And that's like we've seen generics up till now a couple of times. This is what generics build on. So what parametric polymorphism is it's a way to, if you have some scope of execution, a function or a class or any kind of block of code with multiple uses or occurrences of a type variable, you can make that type variable parameterizable. So in the same way that you can have an expression with shared values, you can pull something out as a parameter which gets passed in. This is the same thing, but one level up in the type system. So what happens with this declaration here is you declare a new type variable, and that uses the constructor you see there. It's just called typevar, and then the name of the type variable, and you assign it to a name, and then you can use it any way you could use a normal type. But unlike a normal type, this type variable is not instantiated yet. It's a placeholder for a type to be decided later. And it's powerful because every occurrence of the same variable has to get instantiated by the same type. So what happens in this case, imagine you have a repeat function which just takes some value and gives you an iterable of infinite many copies of that. So it just repeats something as a list. So if you give it an integer, it will give you an infinite sequence of that same integer. If you give it a string, it gives you an infinite sequence of that same string, and so on and so forth. But when you define this function, you don't know what the element type you're going to get is going to be. But you do know that your result is going to be of the same type because you're just repeating it. And this is what type variables and parametric polymorphism lets you express. So you're declaring here that the repeat function is polymorphic. It takes one type variable e, and this type variable will always be the same between the input element and the output iterable element type. So if you call repeat with an integer, you get an iterable of integers, and the iterable integer type will actually be carried forward, and anything that tries to use that will know that these are integers without you having to go and specify that. So that, again, all of this carries through your type inference and everything like that Python or that MyPy keeps track of for you. So yeah, that's basically what happens. And again, here the element type can either be explicitly given, it can be given by a literal. So if you give it a literal 5, MyPy will infer it's an iterable int. If If you give it a literal string, it will infer it's iterable of strings. If you give it a literal of a union type, you will have a an iterable of that union type, and so on and so forth. Yeah. So then, one important feature that actually uses and depends on these parameterized types is generics. So once again, if you're familiar with Java, it's the same kind of idea. If you're familiar with type classes in Haskell, it's more or less kind of the same idea. And how you use them is there's the special generic constructor, which is defined in the typing model, and that takes a list of types you want to be parameterized by. So in this case, there's only one value. We're defining some data structure, which is parameterized by some type T, which might be, maybe you pass that in the constructor, maybe you just declare it, maybe it comes from somewhere else, but for the purposes of this, we don't actually care. We just declare the type variable and then use it. And again, just like the function example, the scope of this particular variable is now the entire class, not just a single method. So, and the scope of it gets introduced by the use of that generic constructor at the top. So we have two functions on the structure, get and set. You'll see that the get method returns a value of the type, the set method expects a value of the type, and if you have a structure of a certain concrete parameter, any use which isn't compatible with the parameterized type of this generic will just fail. So yeah, the top line there, you could maybe declare an empty structure, or maybe it comes from the parameters, however the type is determined. In this case, we're just declaring this is a structure of ints. We can set a 5, it'll be okay because 5 is an int. We can get it, that will give you the current value as an int. But if you try and set a incompatible type, you'll just get that error. And this type information is carried along with this actual instance. So you can have multiple instances of the structure, multiple different variables. Each one has their own unique element type, and they won't get mixed up.
So why is the generic needed? I mean, if you just had a type variable, wouldn't that, after the set 5, wouldn't that already be constrained to be of type int? Because you had the type variable t there.
Yeah.
So
but it is the type variable that actually that introduces that. But it's a feature that works in combination with the generic support.
Yeah, so why do you need the generic as the inheritance
Well, at
declaration?
the moment, that's just the way that you actually introduce the scope of the type variable. So if you didn't have the generic in T, then it would kind of like, it would just use them as separate variables down here, and each function would have, be its own little scope. So if you look at the repeat class over here, the scope of this E is just the single function.
Not the whole module. I thought it was sort of from the whole module onwards.
Yeah. So you do have to declare your type variables, but if you have just a type variable E, you can use it in multiple different functions, but they're not the same. Because remember, different invocations, like every separate invocation repeat can have a different type. So it's its own unique scope. Every time you call that function, the type variable gets instantiated for that call, but only for that call itself.
Okay.
And the next time you call repeat, it might be a completely different function.
Sure. Okay.
So that is what the generic typing introduces. Is it extends the scope, so it's no longer associated with a single call or a single method. It's associated with the entire class and with the entire lifetime of instances of that class.
Okay.
So that's why you can see, for example, once you have an instance of type MyStructureInt, the generic type, you can't, for one call of set have one type and another call of set have another type. Unlike repeat. With repeat, every call can have a different type.
Okay.
But it has to be consistent within the same type. So, with repeat, your input type determines your output type for that call, but every call can, the type that gets carried through can be different. In this case, the entire lifetime of this instance has to stick with the same type. You can't change it unless there's obviously other stuff. You can change it by introducing modifications and stuff. Like that's what happened in that deferred example earlier. But in this case, we're actually declaring this is static. It's not going to change for the lifetime of each instance of this class.
Although it does seem syntactically a little bit unnecessary. Because there's a function syntax. It says def and you inherit a type bar. There's a class syntax and you inherit a type bar. Why do you need the generic? If you're inheriting, well,
At
so
the moment-
it's a parameter in one situation and inheritance in a different one. Why do you
well-
need a generic?
You need some way to indicate that this is going to be a generic type parameter or a generic
Well,
class parameter.
so it's inheriting a type block.
Yeah, but the generic is just there because you need some way to actually put it there. Like if you just put the T on its own there, it means something entirely different. That means that my structure is a subclass of T, not that T is an element of my structure. So for example, if, like over here we have a my structure of int, and int is the parameter that gets instantiated throughout this class. But if we just remove the generic, we'd be saying that my structure is actually an int, which is an entirely different thing. So in some sense, the structure is a bit arbitrary. It's just that you need some way of actually distinguishing it. Like you could have used a different structure, like maybe, I think one of the proposals was to use like, angle brackets like Java does, in which case you wouldn't actually have a word generic, you might just have an angle bracket and then the generic variables and then close angle bracket. But it's a purely syntactic choice at this point. They just decided, okay, this is kind of like the least painful and obstructive syntax, we're just going to go with this. So,
Yeah, I'm just guessing here, but I guess as a human, you kind of think of the class as a sort of scope block. So you'd think that if a type variable is instantiated at some point in that block, it would fix that type variable for the whole block. Whereas, I don't know so much how the AST works, but I guess each method gets bound to the instance as a separate instance, and then maybe if the type variable is only bound within that method block, then different methods could have different ones. So you need to force it to be consistent across the whole instance.
yeah.
You can also imagine that you could have like a parameterizer. So my structure is like a family of types that's parameterized by this T. But you can imagine that within that you might have a method which takes a different, like a repeat method, say, which repeats a different element. So
Yeah.
you couldn't necessarily assume that just because you have like E equals type var within the class body, that means that you want that to be the same thing for the whole class.
Yeah, that's a good example because you can take that repeat method and you can actually just put it as a method in this function. Maybe it's a helper method or a static method or whatever the case may be, but if you don't mention it in the generic at the top, then every call of this method, even with the same instance, can have a different instantiation of the type. So in other words, you can have, for every given type, different input, different output, but they're consistent across all of this method. So it's purely the way they chose the default semantics of the model to work, is that for type variables, the default scope is a callable or a method, and the way that you increase that scope to a class body and an instance lifetime is with or by listing it in generic there. And by just adding or removing the variable as an argument to generic, you change whether the lifetime or the scope of that type variable is across the entire instance or just for specific calls. So you can actually remove the generic there entirely and still keep all the T's inside, but now the scope of each T gets reduced to single calls of those methods, not to the entire lifetime of the entire class. So the generic in the argument there at the top, that is just it's effectively an annotation where you declare which scope and lifetime you want this type variable to have.
Yeah, I'd have it as the guess that second one without the generic there is going to be quite a common gotcha for. It's like having the list in the function declaration, where instead of none, we're like, okay, why is my stuff changing? Why aren't these T's the same? You look at the definition, you think, oh, I'm using the same T's throughout. Why can I call them as different things?
Yeah, so that's something that you can just have to point out right at the front and say that, okay, if you have a class or something that you want to have a type be consistent across the entirety of it, you have to have the generic. So yeah, generic is another example of special. So it's treated specially by the typing module. It's not something you'd be able to use anymore. It's like a core feature of the type system. And yeah, so then the next thing that the system supports, there's quite a few more advanced things which I'll probably just skim through. This is not the meat of it. But one example is you can have bounded types, or rather bounded type variables. Type variables don't necessarily need to be unbounded like the previous one, which can be any time. You can declare a variable like this and say that, okay, k is bounded by the type hashable. And what that means is that k K can only be instantiated to a type which is hashable. But the V value here can be any type. So let's say you're implementing some custom hash table, or maybe with an algorithm, or maybe it's backed by S3 or something, whatever the case may be. You can define your types like this, and then if you ever, try and instantiate this generic type with a key type that isn't hashable, you get a type error at that time. So you can actually type check your types in a sense, or in this particular sense. So for example, you can have a custom hash of strings to sets. That makes sense, it works. But if you try and make a hash of sets to strings, you'll get a type error at type checking time because sets aren't hashable, because they're mutable. If you had an immutable set, it would work, but a mutable set doesn't work. So I'm not actually sure whether the normal dictionary type is defined like this or not, but this is an example of how you would use it. And you can use any boundary type to constrain your type variables to whichever degree you want to. Cool. Any questions so far? Very good. Cool. There's a few other discussion points which I didn't get around to making slides for. One thing to clear up probably right at the start is that you probably got the idea as we were going through this, but the type system in Python, they've been very clear up front about, this is not about making Python statically typed. The language itself is not going to change. It's going to stay just as dynamic as it is, and the type system and all the typing support will always remain optional and compile time with as little impact to the Python runtime as possible. It's also not intended to make Python faster, although it's in theory possible to use these type checks to make a program faster or more performant. As many of you might know, or some of you might know, the kind of type information that you need for performance ends up being almost entirely different and unrelated to the kind of type information that you're interested in when you're trying to make a program correct, or when you're worrying about safety and everything like that. So for the most part, all high-performance code like MyPy and so on will just completely ignore this type of information because it's, for performance reasons, it's effectively useless. It doesn't actually help you at all. And that's not going to change. It's like the goal of this type system is very explicitly correctness, safety, being able to program better and not necessarily make your code run faster. And because it's a graphic...
It wants you to write code a lot faster. You have a good IDE and you make the effort to put an annotation to the dev speed.
That is a very good example because one of the inspirations for the MyPy system and the current system is PyCharm's type checking engine. There's a different PEP, which PEP 482 in fact, which goes into the history of the different type checking or the different semantic models that Python has had up until now. So there's MyPy obviously, but PyCharm actually has its own engine, independent to MyPy, and there's a couple of other tools, all with their own semantics and models and checking and everything. But now that there's kind of like a common system and generally sensibly commonly agreed on model, the systems are actually converging. So MyPy actually used to use quite a different syntax for its own type system because it existed before PEP 484 did. But with the advent of PEP 484, MyPy went and standardized on the PEP 484 syntax, and same thing with the IDEs like IntelliJ and Eclipse and PyCharm and all of those. They also, some of them used to support like older different type annotation syntaxes, like ad hoc ones which are IDE specific. They are now also standardizing on PEP 484. So this is one of the huge booms of this standardization, is that the different existing type checking implementations for Python can now actually start using the same syntax, and you can, once you have your code annotated with this, you can check it with MyPy, or if you're using PyCharm, your IDE will actually check these types for you as well. So I think, I'm not sure how complete IntelliJ support is for PyCharm rather, how complete PyCharm support is for PEP 484. But with the last couple of releases, if you've been using it, you might have noticed every now and then in the release notes, there's like extended support for PEP 484 type annotations, both in terms of generating them with like different intents, and for automatically checking them in the IDE. So you don't actually have to run MyPy. PyCharm will actually just check those things for you as you go along. And yeah, obviously they inform like your code predictions. So one of those features that has always been kind of like a contentious issue between dynamic and static typers, IDE users and that kind of thing, is that in a language like Python, you don't get good predictions for your autocomplete or your code inference or anything like that, because the types are just unknown. Whereas with this type information, you suddenly have all the same rich type information on hand as you develop that you might have in a language like Java. So yeah, the types can definitely make development quicker. That's where the refactoring support and so on helps a lot as well, because now instead of things being implicit and you having to run unit tests to just see what breaks, you can just immediately see all uses of a type, both declared and inferred, and see where things have to be adjusted. So the type system can actually aid you in refactoring by letting you see, for example, where you need to adjust other bits of code that uses the bit of code that you just changed the type of, without them there necessarily being any explicit link between those code. With type inference and everything else, you gain this whole new layer of like mechanized checking of your code, and it's like power armor for your brain. You can suddenly do more without having to think about the low-level details. The computer does that for you. So it checks the. Do that. Cool. Yeah. So that's an important point. And then I think the last thing I want to talk about is the relationship between types and tests, because one of the common criticisms you hear when people talk about, like, say, static typing for dynamic languages is a lot of people will say, why bother with types when you have unit tests? It's like you have unit tests anyway, which exercises all your code. Why do you want to go to more effort now to add all these inconvenient type annotations to your code? So it's just going to overlap and do the same thing. And the answer to that, I think, is that they're not in competition at all, and they might overlap to some extent, but they actually just exist on a continuum. So you can imagine a continuum of like the most ad hoc unit tests on one end of the spectrum, and kind of like very formal like model checking systems and proof checking systems on the other end. And there's this kind of like smooth continuum between kind of like dynamic runtime test-driven checking and kind of like more static model-based type and type checking and related. And you even have, like, along that spectrum, you have things which are kind of like a little bit of both. Like, how many of you have used the system hypothesis for testing? How many of you have heard of quick check in Haskell? Okay, a few more. Cool, so just very briefly, hypothesis is a system where you can, it's a testing library, but instead of writing your tests with concrete examples, like let's say you have some login function, instead of passing a username into that login function, you just tell hypothesis, okay, give me a string. And it will pass that string into your login system. But then, instead of just running it with a single static example, which you have to think of beforehand, it will repeatedly call your test with random examples of strings and try and break it. So you're effectively there giving a type. So you're saying, okay, we're not going to test this function with a value, we're going to test it with type, like a string, which is then randomly instantiated, and your code is exercised with it. And for example, it tries to find values which might crash your code. Like maybe there's a character in that username which gets incorrectly escaped in SQL, and then your test fails. Or there's a terminator which shouldn't be there and the test fails. Or there's a null character and it breaks. Or maybe it doesn't take Unicode, and when you get to a certain Unicode character, your code breaks. There's an infinite variety of things which might happen, which human brain is really bad at actually coming up with. And property-driven testing systems like QuickCheck and hypothesis actually let you check that. It's again this whole thing of having a semantic model, a syntax, and a checker. In this case, the semantic model is not the type system or your unit test, which you kind of like just have an implicit semantic model which is in your head. It's actually this generation of random data according to some parameters, and annotating it in your test of what you want the expected inputs and outputs of this property to be, and then the tool exercises that with random data a million times to see if it can find an example which breaks the semantics of the semantic model you've defined in your code. So all of these things kind of like exist on this continuum, and it's kind of like as your type system gets more powerful, it kind of like eats away at the bottom end of your unit test. You can think of it like that, and that can be very powerful because now,
So you end up, a lot of your boring unit tests, let me pass an integer as a username, okay, my test fails, because I'm expecting a string. A lot of those boring unit tests go away, and you're doing far less work because you're just annotating, this function takes a string. Your type checker, MyPy or whatever, will tell you anywhere where you're not passing a string, so you've vastly restricted the number of things that you need to actually test. So a whole lot of your boring low-value tests, which you need to maintain every time you change your code, all of those go away, and you're left with just your more interesting tests.
So you started by saying that, you know, why have these things? Because you have your unit tests anyway. And the bottom line is you don't have your unit tests anyway.
So yeah, in fact, that's an extremely good counterpoint because you can take MyPy and just point it at some code with no annotation, and you already get useful stuff out of it. And it can catch bugs for stuff that's actually annotated. And the more, for example, common libraries get annotated with types. I didn't even mention the stubs and so on. So by the way, the other thing that MyPy lets you do is you can have interfaces declaring the types for a library, say, like a third-party library, which may not have any type information. But as a community, they have this repository of type declarations for existing code which lacks type declarations, which you can then use, and MyPy will use as the type for that library without you actually having to go and modify the library yourself. So, yeah, for example, you can be using Django, and as the community improves the annotations of the whole Django API, your Django code will just get more checked, even without you having to add a single annotation. It's like a free error bug detector. And I mean, who doesn't like that? And then if you do a little bit of extra work to put those annotations in, you just get more out.
I just want to confirm, you, under syntax, there's like, let's find a nice example, like when you like declare a list, so you set nums is equal to like the brackets with a hash type list. So that hash type in the list, is that defining what type it is?
Say again?
We show the example for
Am I struck?
Found equals hashable.
yeah, like
This one.
no, like where there's like hash type, then but after the type, is that like the type int? Do you have, is that defining it what type it is?
This one. Type one. Okay, yeah. So in this case, it's similar to the example where the list, or for an empty list literal, the type isn't known. Here we're just declaring it that, okay, this my structure is going to be parameterized by int.
And what happens if you leave that out?
It depends on whether the type can actually be inferred or not.
Okay.
So like for example, with the list literal case, if you have a list containing actual ints, you don't have to put that declaration in there because MyPy will infer it. But if you have an empty list, you actually do have to because there's nothing for it to go on.
Okay.
And in the same way here, your my structure, for example, if you can think of my structure as a container of a single value, which you can get and set, maybe like its constructor takes the initial value, and if you pass an initial value, then it will be able to see, okay, you're passing in an int, so this is going to be a my structure of int, even though you don't need to declare the type, it will get inferred. But maybe like if you make the argument to the constructor optional and you don't give an initial value, then you actually have to give a value because otherwise it will be inferred as my structure any. So it tells you, okay, we have a my structure, but I have no idea what's happening in here.
And in your example, I mean, after the set 5, does it not think that it's a int, my struct int, and then throw an error on the set x?
There it actually depends. This is an area, for example, where MyPy's semantic model isn't completely 100% set in stone. They're actually, like, as time goes on, they keep being more sophisticated of the level of runtime information they keep track of. So sometimes, you know, like at the moment, it will actually be smart enough to see that, for example, that will modify the type and it'll actually modify the instance type of that thing after that point. Other times it might not. There's actually, like on the MyPy page, there's a kind of like a list where they kind of like describe at the moment exactly all the things which are currently supported and not supported. And like for example, it's only the cases where you run into unsupported inferences where you sometimes need to give it a little bit of extra help, and you might need to put a cast in there instead because you know what you're doing. But as the system gets more sophisticated, and it does keep on getting more sophisticated, you can actually get rid of those extra annotations and it'll be able to infer more and more as time goes on.
I have a completely different question. Is there any plan to support interfaces?
Zope interfaces.
Well, I mean, Zope is the most used one, so yeah.
Not that I know of. The Python developers' answer will probably be to use ABCs. So I don't think, I'm not aware of any specific plan to support Zope interfaces, but for example, if someone decided to add that to MyPy, it's entirely possible. So PEP 484 doesn't talk about that, but PEP 484 is also open-ended in that they say that, okay, these are the general outlines, but they leave it open to add more supported base types. So that list I had of what's currently supported, like these are just the things officially supported by the PEP, but you can add more. So for example, I know PyCharm, I think, with IntelliJ's own internal typing system, there's probably a few more things in there that you can just put in your program that PyCharm will support, but MyPy might not. And MyPy, I think, for example, still supports the old legacy way of declaring things. So there's a bunch of old, kind of like legacy MyPy declarations which MyPy will support, which you can just use, but they won't work anywhere else as a standard. So yeah, someone might maybe make a plugin for MyPy to support Zope interfaces, and it will just work. We can have a different tool, or it's definitely, it can be supported. Maybe it's already supported others. I'm not sure on that, but it's not explicitly supported in the PEP.
On Zope.interface.typing import implementer or something like that.
So interfaces are interesting because there are also constraints on the types that declare that they implement them.
So, do you know of any nice Vim plugins to refactoring?
No, sadly. I am a Vim user, but these days I use Vim a lot more as a text editor and kind of like just flip between Vim and PyCharm for my IDE features. So I'm going to set up.
PyCharm is a really good Vim plugin.
Does it? Okay.
That's an excellent way to do it. I have shortcuts in PyCharm to just open my current cursor position in Vim and vice versa. So it's I literally flip between them depending on what I need to do at any given second.
Okay, maybe
So I use both.
I tried the Sublime Vim plugin. That wasn't compatible enough for me to work in it. But if the PyCharm one's good, then maybe I can try that.
It has all the stuff, like Control V and like search and replace with Vim, not like shitty IDE.
Okay.
Well, I think one last thing I should mention. This is kind of unrelated, but if you actually go and read the PEPs, PEP 483, PEP 484, and so on, there's quite a few features which I've kind of just skimmed over at the moment, or have not even mentioned. But for example, how many of you know about contravariance and covariance in type systems? Here we go. That is basically, that has to do with how subtypes and supertypes interact and declare with one another. So in the same way that you can have type variables that are bounded, you can declare covariance and contravariance with them as well. And what that means is, for example, in certain signatures like callables, you can actually specify whether, kind of like say, only subtypes of a certain type are acceptable, or only supertypes of a certain type, and etc. and so on. So there's quite a bit of sophistication to the type system beyond just the stuff I've covered here. It's a very complete system. Have any of you used Java, where with Java in generics you can either have an individual type, like an invariant type, or you can say like star extends E, or E extends star, and I forget the syntax. It's stayed in my head very long. It's been a while since I've done Java. But if you have used that, or kind of like you may have touched on it a little bit, that's exactly the same thing. It's something that comes up, not in examples I've shown here, but we do more sophisticated kinds of typing where you need to constrain. In some places of a generic type, you can have this type or any subtypes. It doesn't just have to be the same type. And they can even be mixed, but you have certain invariants that hold over this entire class, and vice versa. So yeah, it's a very rich system, and it keeps, like with the the dynamic example you raised, where it infers the type change based on a set, that kind of intelligence is just going to get on better as the tools and the model gets more sophisticated. So one day we might end up with a kind of like a Haskell-like type system, even with the same kinds of power. We have like pendant typing and many other advanced features which Python doesn't have yet. So it's kind of like, you have this kind of increasing strength of type system from C to Java to kind of like and then Haskell, Actar, and then like those proof systems all the way over there. And kind of like Python is slowly crawling along this line, getting more powerful as time goes on.